This is theory of higher order linear differential equations, and in this video we will be talking about homogeneous linear equations with constant coefficients. So our goal in this section is to obtain a general solution to an nth order differential equation with constant coefficients, and that's what we have right here. We have some experience with our second order differential equations, so we will be feeling that these solutions are very familiar. We will summarize this process. So if we can find n linearly independent solutions to the equation on all reals, and these solutions are y1, y2, and so forth, all the way to y sub n, then we can express a general solution in this form, y of x. We have constant coefficients, so c1 multiplied by y1 of x plus c2 multiplied by y2 of x, and so forth, all the way to our nth constant multiplied by this nth solution. We are going to be using operator notation, and you can see that we will let L be the differential operator defined by L of y, and this means we will be defining L of y as the following. So here you can see that we have a sub n multiplied by the nth derivative of y plus a sub n minus 1 multiplied by the n minus 1th derivative of y, and so forth. And we write our nth order differential equation in operator form as L of y is equal to 0. That is our homogeneous equation. So let's look at our first case when we have distinct real roots. So if the roots are 1, r2, r3, all the way to r sub n of the auxiliary equation are real and distinct, then we will have n solutions to the equation. And these will be y sub 1 of x is e to the r1 of x. Y sub 2 of x is equal to e raised to the r2 of x power. So these are your roots here that you're seeing here, and so forth, all the way to y sub n of x. Then we have our general solution with constant coefficients made up of c sub 1 multiplied by e to the r sub 1 of x, and so forth. So we have these arbitrary constants. Okay, let's take a look at our first example here. So we have the third derivative of y plus 2y double prime minus 8y prime is equal to 0. Our auxiliary equation is r cubed plus 2r squared minus 8r is equal to 0. So we can go ahead and factor in r out of each term. And then, of course, we have r plus 4 multiplied by r minus 2 is equal to 0. So our roots of our auxiliary equation are r equal to 0, r equal to negative 4, and r equal to 2. Therefore, we have our general solution as y equals, and let's go ahead and put y of x equals, and here we'll just have c1 since we have e to the 0 x plus c2 e to the negative 4x plus c3 e to the 2x. Just move that over just a bit. So we have y of x equal to c1 plus c2e to the negative 4x plus c3e to the 2x. Okay. Let's now look at the case when we have complex roots. So if alpha plus I beta is a complex root of the auxiliary equation, then of course we also have the complex conjugate alpha minus I beta is also a root. Now we have two linearly independent solutions. These are y sub 1 of x equals e to the alpha x cosine beta x. And we have y2 of x equals e to the alpha x sine of beta x. And here's our general solution. So here we have our arbitrary constants. And this should be a C2. Make that a little bit. Okay, so those are our arbitrary constants. So let's go ahead and take a look at our example here. We have y triple prime plus 3y double prime plus 28y prime plus 26y is equal to 0. So here, let's go ahead and write our auxiliary equation. So we have r cubed plus 3r squared plus 28r plus 26 is equal to 0. We will do a little bit of algebra so that we can have a common factor of r plus 1. So here we're going to have r cubed plus, and we're going to break this 3r squared up into r squared plus 2r squared, and then break this 28r up into plus 2r plus 26r, and then we still have our 26 is equal to 0. So you can see here that we are going to find a common factor between those two terms, these two terms, and these two terms. And it is a form of factoring by grouping. So we will factor out an r squared here, and we have r plus 1. Factor out a 2r out of the next two terms and be left with an r plus 1. And factor out a 26, and we also have r plus 1. So as you can see, we will factor in r plus 1 out of each one of these terms, and we're left with r squared plus 2r plus 26 is equal to 0. So now we know that either r is equal to -1 or, and we could go ahead and find this r. And here we have r is equal to the opposite of 2 plus or minus the square root of 4 minus 4 times 26 all over 2. And there we will have the opposite of 2 plus or minus the square root of -100 all over 2. And as you can see, we have -1 plus or minus 5i. So now we have our general solution with these roots. There's two of them. There's the third one. And we will write that as y of x is equal to c1e to the -x plus c2e to the -x cosine of 5x plus c3e to the -x sine of 5x. And of course, you can see here that alpha is -1 and beta is equal to 5. Okay, let's take a look at our third case. And that is when we have repeated roots. So if r sub 1 is a root of multiplicity m of the auxiliary equation, then we have m linearly independent solutions, and they are y1 of x equals e to the r1 multiplied by x, y2, and if you'll remember, here we have this extra factor of x, an extra factor of x squared here, and so forth, all the way to x raised to the m minus 1 power. Okay, maybe I won't write that. Okay, and then of course we have our general solution with our arbitrary constants, which is a linear combination of all of our independent solutions. Let's take a look at an example with repeated roots. We have u triple prime plus 9u double prime plus 27u prime minus 27u is equal to 0. Let's go ahead and write our auxiliary equation. So we have r cubed plus, let's go ahead and change this to a minus. Let me go ahead and cross that out, and we will change that to a minus. So we have r cubed minus 9r squared plus 27r minus 27 is equal to 0. And here we have a perfect cube. R minus 3 cubed is equal to 0. So we have just one root of multiplicity 3. So r equal to 3 is a root of multiplicity 3. And then our general solution will be u of x is equal to c1e to the 3x. And now we need to go ahead and include extra factors of x. So we have xe to the 3x plus c3x squared e to the 3x. Okay, so if we have multiplicity 3, so that is why we will have m minus 1, which would be 2, is our power on x that we need. Okay, so now let's go ahead and look at another example. Find a general solution for the differential equation with x as the independent variable. We can go ahead and write our auxiliary equation. We have r to the 4th plus 4r squared plus 4 is equal to 0. And of course, we can factor that as r squared plus 2 all squared equal to 0. So we have double roots here. So we have r squared plus 2 is equal to 0. So we have r equals plus or minus 2i. So that's the square root of 2i. Okay, and so now we have a general solution. We have y of x is equal to c1 cosine of the square root of 2x plus c2x cosine of the square root of 2x plus, and let's go ahead and write this, oops, down here, plus c3x, whoops, that would be sine, c3 sine of the square root of 2x plus c4x sine of the square root of 2x. Okay, let's take a look at our next example. Find a general solution to the homogeneous equation shown below. And here we have our operator notation. And so we can go ahead and write our auxiliary equation. So here we have r minus 1 squared, r multiplied by r plus 3, r squared plus 2r plus 5, all squared is equal to 0. So our roots are r equal to 1, which is a repeated root. We have r equal to -3, and we have r equal to -1 plus or minus 2i, and this is also repeated. So our general solution is y of x is equal to c1 e to the x plus c2 for our repeated root of 1 x e to the x plus c3 e to the -3x plus, we can combine c4 and c5 because c5 would have that extra factor of x, e to the -x cosine of 2x, because that's beta x. And we'll do the same thing with our constants here. C6 plus C7x multiplied by, I'd like to get all of this on one line, the sine of 2x. Okay. Let's take a look at our next example. Find a general solution to the homogeneous equation. We can see that we have our operator notation, and we can write our auxiliary equation as r plus 4 multiplied by r minus 3, r plus 2 cubed, r squared plus 4r plus 5, and that is squared, multiplied by r to the 5th, we can't forget about that, is equal to 0. So here are our roots. As you can see, we have r equal to -4. We have r equal to 3, r equal to -2, and that has multiplicity 3. And here you can see, and you can do that for yourself, we get r equals -2 plus or minus I, and that also has multiplicity, and this multiplicity would be 2. And then we get r equal to 0, and of course you can see we have multiplicity 5. So our general solution is going to be y of x is equal to, so we'll start with our first root of -4, c1 e to the -4x plus c2 e to the 3x plus, let's combine our constants, c3 plus c4x plus c5x squared And that would be multiplied by e to the negative 2x. That's our multiplicity 3 root. Plus, we have c6 plus c7x multiplied by e to the negative 2x cosine of x. There's our alpha and our beta of 1, and alpha was negative 2, plus we can combine our constants here. We have c8 plus c9 multiplied by x, e to the negative 2x sine of x. And now let's go ahead and take our r equal to 0 root of multiplicity 5. So we have our c10 constant plus c11x plus c12x squared plus c13x cubed plus c14. And remember, since it was multiplicity 5, our power of x will be 1 less than that. So that would be c14x to the 4th power. Okay. Let's try one last problem, and this is an IVP. So we can just jump right on in and go ahead and come up with our auxiliary equation, r cubed minus 4r squared plus 7r minus 6 is equal to 0. Factoring, we come up with r minus 2 multiplied by r squared minus 2r plus 3 is equal to 0. And then we have our roots as r equal to 2 and r equal to 1 plus or minus the square root of 2i. So our general solution that we have using these roots, of course, we have y of x is equal to c1 e to the 2x plus c2 cosine root 2x plus c3 sine root 2x, and we will multiply both of those terms by e to the x. We could have separated those, but that's just nice for a change. We're going to go ahead and differentiate that. So we're going to find y prime of x, and that's going to be 2c1 e to the 2x plus, and we'll go ahead and have some constants combined here. So we will have c2, I'm going to have some parentheses, c2 plus c3 root 2 multiplied by the cosine of root 2x plus c3 minus c2 root x, root 2, multiplied by the sine of root 2x and then we will multiply all of that by e to the x. Okay, we can go ahead and do the same thing to find y double prime of x. We have 4c1 e to the 2x plus we have 2c3 root 2 minus c2 cosine of root 2x minus 2c2 root 2 plus c3 sine of root 2x multiplied by e to the x. So using our initial conditions, using our initial conditions, we have that y of 0 is equal to C1 plus C2, and that is equal to 1. And then, so we plug that into this solution, 0 into that, and y prime of 0 is equal to 2C1, you can see that here, plus C2 plus C3 root 2, and that is equal to 0. And then y double prime of 0 is 4C1 minus C2 plus 2C3 root 2 is equal to 0. And solving these equations simultaneously, you will come up with C1 is equal to 1, C2 is equal to 0, and C3 is the opposite of root 2. So with that, substituting these constants into our general solution, we come up with y of x is equal to e to the 2x minus root 2 e to the x sine of root 2x. We do lose our cosine term here since C2 is equal to 0. So we do lose that term. And that concludes this lesson.